All right, so today we will discuss quantum teleportation. So that is quite a nice piece in my opinion, because, I mean, on the one hand it's sort of nice because it's a little bit, makes some reference to science fiction and so on. I mean, here it will have nothing to do with science fiction, it will be purely scientific. But also it combines many of the quantum effects that we've been discussing in the last weeks. So entanglement, superposition, signaling, cloning, all these different notions, they nicely sort of tie in this idea of quantum teleportation. So this is something that was discovered theoretically in 1993 by 6 people. Including, the usuals, Bennett, Brassard, etc. These are names that will often come up here. The first experiments were reported only 5 years later. Okay, so in the 90s there were already some nice capabilities in the lab, in particular with optical systems. And so only 5 years later there were already 2 experiments reporting quantum teleportation in the lab. In a couple of lectures I will dedicate one session just to experiments, because I mean all of these lectures, they are pretty abstract, so I guess it's nice for you also to see that all of this can be implemented in the lab, right? So we will discuss that. What else should I say? Yeah, maybe I can say that by now, so this quantum teleportation, it has been done not only with photons, but also with atoms and, different degrees of freedom. And so it's really now one of the sort of building blocks of quantum information. So what is the goal? Well, the goal is to send some quantum information without having access to a quantum channel. Okay, and we will use only a classical channel. Okay, so let me think. Yeah, okay, maybe I draw it here. So we will have Alice here. So Alice has a piece of quantum information. So that will be some particle here. That is, we are just going to be looking at a qubit here. So this is a generic qubit state. So this is the piece of quantum information that Alice would like to send to Bob, who is far away, right? And so if you had access to a quantum channel, so imagine that this qubit here is encoded in the polarization of one photon. Okay, then you can send this quantum information from A to B by using, for instance, an optical fiber. Okay, you put in the photon and then it will arrive on the other end. But an optical fiber is a quantum channel, right? It's a channel through which you can really send whatever quantum state. So let's admit it's a perfect fiber, right? So then if you have some state at the input, you also have it on the other side. Okay? Now here we cannot do that, right? You see, in particular, if I have an optical fiber between A and B and I put my photon in and it comes out at the other end, well, I guess you would all agree that this has nothing to do with teleportation. This is just a direct transmission of a particle from A to B. And because the particle has a continuous trajectory between A and B, and because this particle carries this quantum information, it is fair to say that the quantum information, my qubit here, travels continuously from A to B, right? So at every point here between A and B, I can say, okay, I interrupt here, and I could have my qubit there with the quantum information. So that is just the direct communication. So direct communication is really the idea that you have a continuous trajectory. Now, teleportation, it's the idea that, at some point, my quantum information will disappear from A, and later on, it will reappear in B. But somehow, this quantum information will not travel through, continuous set of points between A and B. So it will be a discontinuous trajectory. At some point, it will disappear here, and later on, it will reappear there. Okay, so that's the idea. All right. I will nevertheless need this classical channel. Okay, so it will be important that Alice can call Bob on the phone. Okay, or can write something on the internet that then Bob can read. But this is only classical information, right? So, and of course I cannot directly use that channel, because if I try to measure that state here, which is a priori unknown to me, right? So if I would try to measure that state, well, you already know now that a measurement will necessarily perturb this quantum information. I will learn only one bit of information about that state. And so even if I try to learn some information here and tell this classical information to Bob, that could never work, right? I would never be able to recover psi here in the end, right? So I need to do something else, right, in order to preserve the quantum coherence. All right. So now this brings me to the second point, which is that what will be important also is that what we are going to teleport is not mass or energy, okay? What we are going to teleport is information. So information is this state. So what that means is that at Bob, there will be a particle. Imagine, let's say, another photon, okay? And this photon will be the one on which my information will be teleported to, okay? So it's not that this photon here will disappear, so that energy will disappear here and that it will reappear there. No, what's going to happen is that the information about that is encoded on this photon will disappear and will later reappear on this one. Okay, that is the idea. Okay, so this is a difference with Star Trek or whatever, science fiction teleportation you can imagine. Okay, good. So how do we do it? Okay, so if I would just have access to these two particles here and my classical channels, that wouldn't work. Okay, you see, intuitively, I need some sort of connection between A and B to mediate the protocol. And so what I'm going to use is I'm going to use entanglement. Okay, so these two particles here, they will be entangled in some state phi plus. Okay. So you see, at this point, one could say, okay, but then I have a sort of quantum connection between A and B. That is true, but the point is that this connection, this entangled state, it could have been shared by A and B since many years ago, right? So for instance, if B went into some intergalactic trip, right? So when he left Earth, he could have taken half of this entangled pair here, and the other particle would stay with Alice on Earth. Okay, so this is just some sort of resource that you need from the beginning, but you see, this resource has nothing to do with the quantum information I want to send, right? So Bob leaves Earth here, takes half of his entangled particles, And 10 or 20 years later, Alice decides what piece of quantum information has to be teleported to Bob, okay? And this entanglement, of course, this is some correlation that is, you know, it's there between the two particles, but there is nothing physical here, right? So I draw a wiggly line to show this, you know, spooky action at a distance, this connection, but this is nothing like a fiber or cable, right? This is just some abstract correlation in the Hilbert space. All right, so now, well, we have essentially everything except for the fact that you see now, if I really want to send that quantum state from this particle to this one, well, obviously I need to create some sort of interaction between these two, right? That's the idea. And in fact, so, you know, or you can understand already intuitively, I'll have to somehow entangle these two in a way, right? That is the idea. And I will do that by performing an entangled measurement on these two particles, okay? But okay, let's see how it goes. So now let us start slowly, and we are going to just put indices now in order to make everything clear. Because we have now 3 quantum subsystems, so we need to be a little bit careful. So here we have our Bell state. And so you see now I can write the total state. So this is the total state of this system, which has subsystem little a, then capital A, capital B. Little a is here, and capital AB are for this entangled pair, okay? So what is the state here? Well, this is an alpha 0A plus a beta 1A. Okay, then there is a tensor product, and here there is a phi plus for AB. Okay, so now I can just rewrite all that, and I can write okay. And yes, okay, to be consistent, there should be a 1 over root 2 here in front. Okay, so here you see I have cats with 3 subsystems, which are just A, capital B. Okay, I don't write this everywhere. Okay? So at this point, I didn't do anything, right? I just used linearity, I expanded, I wrote the initial state. Now, okay, so now comes the next ingredient, which is this interaction I mentioned before. So now the idea is that Alice's 2 particles will have to be measured together, and the basis of the measurement has to be an entangled one, right? Well, you see immediately that if I would make some measurement on that qubit and another measurement separated on that one, but there is no reason why that particle should get back this quantum information psi, right? So this could only happen if somehow these 2 now become entangled, right? If they interact. And so the measurement I'm going to perform here is the so-called Bell state measurement. It's a measurement that has 4 possible outcomes, and these 4 possible outcomes, they are the 4 Bell states. So let me move that label to here, and you see the outcome could be it could be phi plus, it could be phi minus, it could be psi plus, it could be psi minus. Okay, so I don't write them again, but these are the 4 Bell states, and well, as you remember, they form an orthonormal basis, right, of the system of 2 qubits, and therefore I can make a measurement on them, right? Maybe it is not clear to you what physically this measurement means. That we will see in a couple of weeks, but let's just think abstractly, right? Because they form a basis, I can certainly do something like this, okay? So now, what I would like to do is for each of these 4 possible cases, I would like to understand what is the state of that particle, okay? And so to do that, I can just work it out from this equation here. Okay, so how would I do that? Well, you see, at this point, I wrote everything in the computational basis, right? Where I have a tensor product of A, capital B. Now, in order to know or to understand what is going to be first the statistics of this measurement and then the state prepared here, it is enough that I do a change of basis. Okay, so for the point is for the first 2 systems, which are those that are going to be measured here in this Bell state measurement. For these 2, it would be more convenient for me to re-express everything in the basis of the Bell states. Okay, because that is the basis of the measurement. Okay. So I hope this is clear, no? But if I have a state 0 of a single qubit, and I make a sigma x measurement, and I want to understand what the statistics are going to be, well, it is, either I just calculate things directly in that basis, or I could rewrite that state in the x basis, right? So this is the state plus, minus, okay? Normalized. So if I write the state like this, now it's expressed as a superposition of the eigenstates of that measurement, okay? And if I see it like this, I know exactly what's going to happen, right? So I'll do exactly the same trick here. I will just rewrite my state. It's just a change of coordinates, so it's still the same state, but I use the basis of my measurement, okay? So now comes a step that is ever so slightly tedious, but okay, it's not very, very difficult. I mean, there are several ways of doing it, but one way that is relatively convenient would be to say that if I have 0, 0, okay, how does that state look like in the Bell basis? Well, this is simply 1 over root 2 times phi plus phi minus. Okay, because this is a 0, 0 plus 1, 1. This is a 0, 0 minus 1, 1. So if I do it like this, I get a 0, 0. Okay, and similarly, 1, 1 would be the same, but with a minus sign. Okay, so that's one way to do it. It's pretty simple. And now, okay, so my state will look like this. So you see, the 0, 0 and the 1, 1, they are going to give me some phi plus, right? So first, I will surely have a first term here, where maybe let me write it with the subscripts now. So this is a capital A. So this is the state phi plus. And for this one, I have a contribution from here. Okay, so it means that now the state of the B particle has to come with it will be in the state 0, right? And it comes with a coefficient alpha, okay? But, I mean, this phi plus, it has also a contribution from here, right? From the 1, 1. And therefore, here it will come with a beta 1. Okay? And that is for subsystem B now. all right? Of course, has no contribution from these two terms because 1, 0 and 0, 1, they are orthogonal to phi plus, right? So, okay, good. So now I can continue. I write phi minus. So phi minus, it's the same idea. So I get an alpha 0. Now I also get a beta 1 from this one, but because it's a phi minus, I get a minus beta 1 this time. Okay, now I did something silly because I need another line here, but okay, I'll just write it below. So if I continue my equation here, so I have a plus psi plus. This is A, capital A. So psi plus is a 0, 1 plus 1, 0. So it comes from here, right? Here I have an alpha 1, B. And from there I have a beta 0. And so finally the last term is the psi minus, and that comes with a alpha 1b minus beta 0. Okay, and here I can close the bracket. And I have a 1/2 coefficient because of this 1 over root 2 here, and because I inserted everywhere these Bell states, I get another 1 over root 2, right? So, but you can check that this thing is properly normalized, right? It has 4 terms. Each term is normalized. There are 4 of them, so the coefficient is 1/2, indeed. All right. Any questions so far? No. This is simple. Okay, but now you see it's beautiful because we have essentially finished, right? Because now take a look what happens when the output of the measurement is phi plus. Aha, okay. So the state of Bob's particle, it is just exactly psi. Okay. So in that case, well, the state of Bob's particle is exactly the initial state of Alice, right? So that's nice, but of course, this case here has a coefficient 1/2, so it happens with probability 1 over 4, right? Well, this is not so astonishing. There are 4 outputs here, and in fact, all of them are equally likely, okay? So now let's look at the other cases, right? So you see the other cases, there is always something reminiscent of the structure of the initial state, but it's not quite right. It's not quite right, okay? It's not exactly the good state. It's almost the good state. So this one, for instance, it's correct up to this flip here. So that state would actually be a sigma z. It would be a sigma z applied on psi. Okay? Now what would that one be? Well, that would be a sigma x applied on psi, and that one would be so that would be a sigma z applied on psi b and a sigma x in front. Okay, and so if you remember the algebra of these Pauli matrices, this is something like a sigma y. Okay. Okay, so you see, this is interesting, right? I mean, when we do this change of basis, right, from that state where it is absolutely not clear that there is anything about any information about the state psi encoded in that third subsystem, but when we go to the Bell state basis, the basis of the measurement of Alice, then it becomes really clear that for each possible outcome of that measurement, the final state of Bob has exactly the structure of the initial state, just with some sort of correction on it, okay? All right, so now the point will be that Alice is going to tell Bob what is the result of her measurement, right? And that information is just 2 bits, right? There are 4 possibilities. And so if Alice gets the output phi plus, okay, then the particle of Bob is in the state psi, okay, so then it's already the good one. So what Bob is going to do, so Bob will now do a final correction or transformation, and that transformation will just be the identity. So of course he has to do nothing because he has already the correct state. So if the outcome was phi minus, then what we saw is that Bob has the correct state up to a sigma z in front. But remember, sigma z squares to the identity. So the transformation that Bob has to apply is a sigma z. Okay? Because then he applies sigma z onto sigma z psi, and that is just psi. Okay? And now, of course, it's just similar for the rest, right? So this is a sigma x psi. So here Bob is going to do a sigma x. And for the last one, this is sigma x, sigma z psi. So Bob will have to do a sigma x followed by a sigma z. All right? And then, in all cases, in the end, he gets psi. Okay? So here is one important point to notice. It is that, remark. So the point is that this, maybe instead of transformation, let's say that this is a sort of correction. Okay? So the correction of B does not depend on psi. Okay? It only depends on the result of Alice's measurement, right? So it does not depend on psi. It's only on A's measurement outcome. Okay? Yeah, good. We can also write here what are the relative probabilities of seeing each of these 4 cases. And of course, this is uniform, right? So it's 1/4 for each one. Exactly, yes. So the information that Alice has to send is just which of these 4 she measured, right? Now, of course, she could, you see, there would also be a problem if somehow Alice could in advance tell which state it's going to be, right? But of course that cannot be because all the outputs are equally likely, right? Yes? Yes?
Why Bob would use the same correction as sigma?
Ah, it is not the same. No, here it is a sigma z, and here it is a sigma x.
Oh, okay.
Yeah, sorry, my writing is not optimal, but yeah, you see it has to be a different one, right? Because that state is not the same as that one. It would be a huge problem if it was the same here, indeed. Yeah. Because then it would mean that Alice would not have to send 2 bits of communication, only a trit, right? Only a ternary information. And we will, let's see, if we have time later, we will give the argument as to why these 2 bits of communication are strictly necessary. You cannot do with less. Okay, but we have a couple of things to discuss now about this protocol. But maybe just to make it complete before, I should add, well, I'll add that thing here. So this is my classical communication. This is two bits, okay? And so then, to conclude the protocol, well, Bob here will implement the correction, okay, based on this information, and then finally he gets the state psi. Okay, yes?
What happens if we have density matrices instead of pure state?
Okay, yeah, good question. Well, so your density matrix, you can always express it as a convex combination of pure states, right? Now, all of this is linear, right? And so if you start with a collection of pure states mixed with some probabilities, you will get the same on the other side if you do everything well. So you can also teleport a density matrix. Does it make sense? So you see, think of a density matrix like this. With some probability, you have a pure state psi. Okay, in those cases, it works like this, right? Then you have psi on the other end. Now with some other probability, you have a state phi, okay? Then it will also just go like this, right? And so then on average, what state you have reconstructed on the other hand, your density matrix.
Basically, what would change this, like the left column, like the probabilities will change, basically. Or not really?
No. It's a good question. It's a good question, but the answer is no. It won't change. Okay, so let's now. Okay, if you have more questions, please ask, or during the break. It's a little bit difficult to digest, maybe at just like this in 20 minutes. But well, I guess you agree that the math is pretty trivial here. Okay, there is this change of bases, but well, okay, not very difficult. But now there are lots of interesting consequences of this protocol. Like, for instance, what happens if you put a density matrix. Okay, but now Okay, so let's maybe look at these one after the other. Okay, so the first thing that one may wonder is, let me think in which order I should do these. Let me check my notes. I think I did it in the right order there. Okay, so the first point is that there is this protocol here respects no signaling. Okay, so again, what is no signaling? It's the idea that you should prevent any form of instantaneous communication from A to B. Okay? So how would that work? No, so okay, no, sorry. No, okay, maybe I start with this. So imagine Alice tries to do this signaling, right? To send instantaneously some information to B. So there are in fact two ways in which she can do this, right? So she can do this by choosing the state to be teleported, right? So she can encode one bit in it. Now, why is the protocol no signaling, right? Because a priori Bob recovers the state of Alice in the end, right? So in principle, one has to check really at what speed the information goes here. Now, the point is that it is fundamental that the communication from A arrives at B, okay? And that B does this correction. You see, I mean, because intuitively you could think, even if I don't know, even if Bob doesn't know what is the result of the measurement, right? I could already say that here in a quarter of the cases, he's got the information correct. And in the three other cases, okay, the information is somehow there, but okay, although it's not quite correct, there is still a trace of it, right? So Bob could try to make a measurement on his particle before the communication arrives, and you know, if he could find a trace of psi there, even the slightest information about psi, that would be signaling, right? Because it would be completely instantaneous. Okay, so we have to see so that without, or maybe let's say like this, so before receiving the communication, that is the classical communication from A, okay, B knows absolutely nothing about psi. Okay, so this we have to make sure, right? Otherwise the protocol would lead to some signaling. So how do I do that? Well, I need to see. So the question is, what is the state of Bob? Okay, so this will have to be a density matrix. Okay, and now, so imagine what is, so how can we figure out what is the state of Bob before the communication arrives? Well, okay, so, you have an idea? Sorry, I saw a movement somewhere, but any ideas? Okay, so I suggest you one idea. So we take this equation here, which describes completely the state of A and B, right? And we trace out A, right? If we do that, we should indeed get the state of Bob, right? Before the communication, right? Because before the communication, Bob doesn't know if it's this piece, that piece, this piece, or that piece, right? So to describe that state, I should make a probabilistic mixture of these 4 states, right? Because this is what Bob has, and they are all equally likely. So the state is 1 over 4. So first, the state would be psi. Okay, it's a density matrix, right? So I have to write the projector on psi. Then comes this one. So then it would be sigma z psi. Then it's that one, so it would be sigma x psi psi sigma x. And finally, let's hope I can write it here. So this will be a x z psi psi z x. And okay, I just close the thing here. So you agree, no? That's the correct thing. Okay, so that looks like a messy computation, no? I mean, one can certainly do it. Now, I claim that it's pretty trivial to find out what it is. Maybe let's not say trivial, but pretty immediate. So any idea what this computation should be equal to? So I give you a hint. No? So each of the Paulis we know we can view as a rotation, right? We saw that sigma x is like a NOT gate. Okay, so it would be a rotation around the x-axis. Similarly, sigma z is a rotation around the z-axis. And remember, that thing is essentially like a sigma y. Okay, so it's a rotation around the y-axis of the sphere. So you see, in a sense, what I'm doing here is that I have some vector on the sphere, and I mix it with the sort of rotation of the vector around x, y, z. So it's something that is pretty uniform, like it's a sort of scrambling of my vector. So if I scramble, yes, I heard something that sounded right. So if I scramble all the information there, I get no more information somehow, right? And so the state I get out of it is the completely mixed state. So this is just the identity matrix normalized, right? So it's the maximally mixed state. It's not obvious when you see it like this. You can make the calculation if you want explicitly, and you will find that it's the identity. Okay. This is beautiful. Now, I could also tell you that you could have guessed right from the very beginning that the state must be the identity. And this you can do just by looking at that picture over there. Okay, so would you see a way to justify that from the picture? So think of it like this. So B has a particle that is entangled with one on Alice's side, right? Now we are interested in the state of B before the measurement results arrive, right? But that could even be without the measurement happening at all, right? So it could just be the reduced state of Bob's particle there. And Bob would have no idea of what's going on Alice's side. Right? And so then the state, so how do I describe that reduced state of Bob? Well, it's half of a maximally entangled state, right? And so what is the reduced state of half of a maximally entangled state? Well, it is the identity, right? And so you see, so here we did sort of, one stone, two shots, right? So first, with this argument, we show that indeed, I mean, on mass here, even though we didn't do it, but this is correct, right? The state of Bob before the communication arrives has to be the identity. Okay. Moreover, in fact, this is very important that it is, right? Because Bob, you see, before the communication arrives, Bob doesn't even know that Alice made a measurement or not, right? And so that could be another way for Alice to signal to Bob, not necessarily by trying to teleport some information, but by deciding to do the measurement or not do the measurement, right? So when she presses here, or she makes these two particles interact in the Bell state measurement, that is also a choice, right? She could decide to do it or not. And if that action had an influence on Bob, that would also be signaling, right? Because you see, because once the measurement is done, let's say you project here, well, because of the form of this quantum state, there is, because there is this entanglement somehow, well, then the state of Bob is immediately projected onto this, right? So there is, via this entanglement, there is some sort of instantaneous collapse of the state of Bob, right? Because, the result of that measurement is probabilistic, whether you happen to be here, there, or there. And in each case, Bob's state is immediately collapsed to, one of these four possibilities. So there is some sort of spooky action at a distance, right? Because the particles of A and B are entangled. However, it is impossible for A and B to use these correlations to signal, right? That's the important thing. Does it make sense? Okay, I guess it's a good time to make a break, and I let you think about it and ask questions. Okay, good. So I hope you had time to think a bit about all of this thing here. So any other question on this? No, you are all more or less happy for now. Okay, good. All right. So I would like to continue discussing the implications of this protocol, and in particular verify that it is consistent with, several ideas that we have been discussing in the first lectures. So the first one is that the protocol should be compatible with the idea of no signaling, right? That there is no instantaneous communication. And so here we argued that if Bob, could get some information about psi before receiving the communication, that would be a form of signaling. So we need to check that this is impossible. And here we check that indeed the particle of Bob is in a state that is the identity before the measurement arrives, and therefore has absolutely no trace about psi, right? So if Bob tries to cheat by trying to get some information before the communication arrives, that just doesn't work. Okay, so maybe I continue here. So there is in fact a second part to this, which is that it's the fact that whether A actually makes the Bell state measurement or not does not change Bob's state. Okay? So that is the argument that so in a sense, you see, here I calculated the state of Bob, but you see, because I took this particular structure here, I sort of, because I took it from there, right? Here I kind of assumed that Alice made the measurement, right? And therefore, Alice made the measurement, then you forget about the result, and then you have this mixture of 4 terms right here. And then if Alice did not do the measurement, right, well then we argued that the state of Bob is just the reduced state of a maximally entangled pair, and that has to be the identity, right? And so that identity is the same as this identity, because there is just one identity. And so therefore, you see, that also doesn't work, right? So Alice cannot signal by deciding to make the Bell state measurement or not. So this is also no signaling here. All right, now let's do a second remark. This is point 2. This is the connection to no cloning. Okay, so we saw last time that there is absolutely, so it's impossible to perfectly clone quantum information, or to make a copy of it. So we argued that if you take one copy of a system, you cannot make 2 copies of it that are perfect, right? However, you see that if you could do something like this, right? If you could take psi and get out of it psi and something else here that somehow depends on psi, right? That in fact would also be a problem. And in fact you can understand, no? Because then I could just repeat that thing, right? So this would give me psi and some rho psi and so on, right? And so if that second object here has a little bit of information on psi, because by continuing this line here, I can get arbitrarily many copies of that guy. I could reconstruct that state by tomography. And so if it depends on psi, I can know what it is, right? So I can reconstruct psi and then I can make arbitrarily many copies. So it is very important that if I have a process that takes psi and puts it back here, then on the second system, there should be something that is not a function of psi. Okay? So that state here must have absolutely no information on psi. And this is important for us, right? Because we have a protocol where the state psi is initially on Alice, right? And in the end, it's on Bob. Now, we need really to verify that on Alice's side, there is no trace left of what psi is, right? If there was the slightest information about psi in Alice's system, well, we may have a problem with this no cloning theorem, right? So the verification of this, there will be only one, in fact. So we have to check that no information, so it's really no information at all about psi is left at A. Okay? So what does A have? Well, A makes the Bell state measurement, right? Well, this is important because if A doesn't do the Bell state measurement, then there is no information on psi at B, right? So in any case, we just take it for granted that A does the Bell state measurement. Then we have psi on B, right, modulo the corrections. And then, so what is the state left on A? Well, so Alice here made a projective measurement, right? So now the state of the system after that measurement is one of the 4 Bell states. And of course, none of these Bell states depend on psi, right? So that's okay, right? I mean, the dependence on psi would be some dependence on alpha and beta, right? This is what defines psi. But obviously, the Bell states do not depend on psi. And more importantly, also the statistics of the measurement doesn't depend on psi, okay? Because the statistics of the measurement is just always uniform, right? For every psi, you get a 25% chance of finding this, or finding that, or that, or that, right? So that is how, you know, this is what makes it compatible with no cloning. So this is because the statistics statistics of Bell state measurement is uniform for all psi. All right. Let me think. Yes. So maybe I can also add a third comment here. The third comment is that the protocol works for any, and you know, in principle, unknown state psi. So you see, the fact that it works for all state psi, but if the state is known to you, right? If you know what is alpha and beta, but of course then you can teleport it, right? Even with just a classical channel, because Alice just calls Bob and says what is alpha and what is beta, and then Bob can prepare arbitrarily many copies. Okay, so it's like in the no cloning theorem, right? What is important is that you want a mechanism or a protocol that works for any state, even if you don't know that state, right? And so here, the protocol works for any state psi that even if it's not known, right? And because you see the operation, well, the protocol is always the same. It does not depend on what psi is. All right. And then I would say, yeah, it's really teleportation. Because you see that at the moment where you do the Bell state measurement, somehow the information that was initially on Alice in this subsystem, it has been immediately transferred to the second subsystem, or to the third subsystem, right? The one of Bob. Right? I mean, at the moment where you do this measurement, well, you are just left in one of these four possibilities here. There is not even a trace of psi left on A. And on the other hand, well, the information about psi is immediately somehow teleported to Bob, right? It's in there. Now, of course, if it was just teleported like this, you see, like in this case here, that would be a problem, right? It would be signaling. So therefore, if you want to prevent the signaling, it is really fundamental that you have this sort of scrambling of the information, right? That it's either that, or that, right? It is really a scrambling of that information about psi, right? And this scrambling is random. It is random because it is controlled by the result of that Bell state measurement. And the result of that measurement is random, it's uniform, right? So this is another way, you see, to argue that, you know, when you see it like this, the randomness of quantum mechanics, right? The fact that it is absolutely impossible to tell whether your particular experimental round will give you this, that, or that. this is fundamental, because if you could somehow predict which one is going to be, even with the slightest bias, then you could signal. Okay, so somehow the randomness of quantum mechanics, it's not just there, not to please people like Einstein. It is there to save compatibility with relativity. Okay, because if you see this entanglement is this sort of spooky action at a distance, and so if the measurements that you do on these subsystems, they were not random, if you could somehow control them, then you could signal. So the randomness is really there to enforce no signaling. Okay, so it's another take on it, but I guess it's, in a sense, it's more illuminating than just saying, okay, it is random because it's random. So I would say it's random because it has to be. Okay, otherwise it would have tremendously dramatic consequences for physics. All right. Okay, good. Okay, so now you know everything about teleportation. Oh, good. We still have quite some time. So in the tutorials, I suggest that you look at two things. So the first one is, as someone already asked during the break, is, you see, I mean, all of this is nice theory, but of course, if you try to make this now in an experiment, there will be imperfection. And the first imperfections is that in an experiment, there are no pure states. Okay, there are always errors, there are always little imperfections, there are just no pure states, and there will be density matrices. So density matrices that look very much like these states here and that one, but yet they are density matrices. Now again, the linearity of quantum mechanics is important, right? So if you have something, so let's imagine first that you teleport a density matrix instead of a pure state, right? Now because everything is linear, right? If your state here looks very much like that one, and if you do everything correct, your final state will just be exactly the same as here, so it will also look really like this one. Okay, so then this is okay. Now, a bit more tricky is when you have imperfections here, right, in this entangled state. Now, so imagine that your entangled state here looks like this one, but with some probability it's different. There is some noise to it, right? Now, you still see by linearity that everything works because, most of the time you have something like this. So then most of the time you teleport the right density matrix. Now with some little probability there are errors, and so maybe in those cases things go wrong, you don't teleport the right thing. But again, because of linearity, the probabilities of error here is the same as the probability of error there, and so therefore everything still works. Now, maybe a more interesting question is the one that says, okay, but if I have a protocol that has errors in the end, how can I justify that this is really teleportation? Because maybe then, if I would do some other strategy whereby I try to get first some classical information about that state, and I then send that classical information to the other side. Okay, we already argued that this cannot be a perfect protocol, but maybe the errors that I introduce in that protocol are, very weak. Maybe they are comparable to some noisy teleportation. So in the exercises, I suggest you show that, there is in general a pretty big gap. Okay, and in fact, so the first exercise is you see, in a sense, the question is, if you make a measurement on this unknown quantum state here, what is the best fidelity for your state that you will recreate out of it? Okay, so that means if you, so for instance, you could imagine doing a random measurement because a priori you have no information about this state here. And so you just do a random measurement in one basis, and then depending on the result, you are going to say that it's the eigenstate of that corresponds to that result. That is in fact the best thing you can do. And so if you do that, well, you can prove that the best fidelity you have in estimating that state, it is 2 out of 3, right? So it's 2/3. And so that means that now in an experiment, for instance, if you prove that the fidelity between this input state here and the final state here is larger than 2/3, then you have proven that there is some genuine teleportation that is going on. Okay, so this is how you can argue that the thing works well even in practice, right? Does it make sense? Okay, good. So that justifies the first exercise. Now the second exercise is a sort of fun extension of this protocol. So here we said, okay, so here we have a particle which is prepared in this pure state, okay, and then it will be teleported. We also argued that if I have a mixed state here, it should also be teleported, right? Because all the individual pure components are teleported like this. Now, what happens if that particle here, it is entangled with another one? Okay? So if I have, imagine I have another phi plus here. And now this guy here I call C. This is Charlie. Okay, so you see the question is, what is going to be the connection between that particle and this one once you post-select on one of these 4 results? Well, I think you can just, in fact, you can just follow what teleportation says, no? It says that the quantum information of that particle will be teleported to this one. So if this particle is entangled with another one, well then at the end of the day, this particle will be entangled with this one. Okay? And that is what is going to happen. And so that is the protocol of teleportation of entanglement, but we call it entanglement swapping. And yeah, in a sense, that is also a fun protocol because you have 2 particles, that one and this one, that have never seen each other, right? They might be very far in distant galaxies. But somehow, if you have this configuration here, you can get them entangled, right? Without them even touching themselves, right? Of course, that can only work if this one is entangled with this, if that one is entangled with this one, and then these 2 somehow are projected into some entangled basis, right? Yes. So doing the exercise with this is, it just amounts to replace this thing now with a phi plus. It's a little bit more complicated because you have another qubit, so you have a 4-qubit system. But okay, the calculation is really just the same. So let you look at this. All right. So now, if there are no more questions on this, I tell you about another quantum information protocol that has some similarities with teleportation it's a little bit less spectacular somehow. But, I erased this. Okay, never mind. So this is a protocol known as dense coding. Okay, this is even older than teleportation. I think it's maybe 91 or something like this. Was invented by someone called Wiesner, who, had a couple of brilliant ideas like this one in the early 90s, but then somehow completely disappeared from the map. In fact, he had another nice idea, which is also one of these very early works that started quantum information, but somehow, it's not so much investigated anymore. But the idea is beautiful. It's the idea of quantum money. Okay, so with money, one of the big problems is that people can make fake money, right? And so the idea is, because you take a banknote, everyone has banknotes, you look at it, and if you're good art maker, you make a copy that is essentially perfect, right? Now, what is the idea of quantum money? So if you encode a banknote in a quantum state, so each banknote corresponds, each banknote has a number, right? But of course, the problem is that everyone can read these numbers and then you copy them. So even by checking the identity of your banknote, it's not enough, right? But if this identity was quantum, right, then there is the idea that, one cannot go and make a measurement to learn that quantum state, right? Because then you are going to disturb the state, okay? So that's why you could imagine a scheme that prevents, counterfeiting money, okay? Of course, it would be a bit complicated if all banknotes have to be, a collection of qubits and so on. But also, you see, conceptually, the idea is nice, right, of this quantum money. Okay, but let's go back to this dense coding. And so here, the question, so this is not quantum for once, this is question. The question is how much classical information can one qubit carry. Okay. Now, again, so entanglement will be useful in this. Now, in fact, there are two answers to this question. The first is the answer in the case where you have no entanglement, right? So without entanglement. So you see, you try to send classical information from A to B, and here we say A and B do not share initial entanglement, right? So without entanglement, the answer is 1 bit. So 1 bit of classical information. So this is something that is known as Holevo's theorem or Holevo's bound. So it looks like a simple thing, no? So if I have a qubit, well, a qubit, it's a alpha 0 plus a beta 1. Okay, so we argued that if I make a measurement in a basis, the result is binary, and so I can only get 1 bit of it. That seems obvious. Now you could imagine more sophisticated measurements like POVMs or something like this. And you can actually prove this theorem, which is actually, it's bloody hard to prove. It's not something simple. It's actually because it also proves something a little bit more general. But okay, never mind. So we will take it for granted. Also because it's relatively intuitive here. Okay. Now here comes the fun part. So if you have, so with shared entanglement, okay, you can get 2 bits. Oops. So 2 bits of classical information. Okay, so you have a sort of boost in the capacity, right? So you send one system that is just a binary one, and ooh la la. Sorry, I see some lights. Well, never mind. Some accident probably. So let's focus back on this. So if you have shared entanglement, now you can increase the capacity. That of course this is very non-classical, right? Because if I send classical information from A to B, even if I have some sort of pre-established strategy with my partner, right? If I send 1 bit of information, he learns 1 bit of information, right? It doesn't matter that we agree on, previous things. Now, agreeing on previous things, it's like somehow sharing correlated systems, okay? And so classically, whether I share or do not share something with my partner doesn't change the capacity, right? If I send 1 bit, he will learn 1 bit. Now, with quantum systems, it's quite different. So if I have no shared quantum information, right, then the capacity is 1 bit. This is this Holevo theorem. But if I have pre-shared entanglement, right, and again, it's like in teleportation, this pre-shared entanglement doesn't depend at all on the communication I want to send. It's just some resource I have there in order to boost my protocol, okay? But if I have this pre-shared entanglement, I can double the capacity. So it's a sort of dense coding of quantum information. 2 bits into 1 qubit. And so here is how it works. So I have A and B. So again, they share some entangled state. Let me go say again, this is a phi plus, okay? And now the point will be that Alice would like to communicate 2 bits. Okay, so these are 2 bits of Alice. I call them C0 and C1. So there are 4 possibilities. There is 0, 0, 0, 1, 1, 0, 1, 1. Okay. Now, here is the idea of the protocol. So now it is Alice that will first perform a transformation on her qubit. Okay. Now, the transformation, this will be, I hope, reminiscent. Don't know. Do you have lecturers that use knives to write on the board? Or unbelievable. Each Tuesday there are new marks on these boards. It's crazy. Okay, never mind. Yes, let's do it like this. Okay, so you see, again, there are 4 possible transformations of the qubit. Now it is Alice that can use them, okay? And so these are local transformations applied to that particle, but in fact they will change the global state, okay? And in fact we can see that right away. So this is the, okay, so this is the shared state, okay? Now, if Alice applies identity, well, obviously the state remains phi plus, right? Now, if the transformation is sigma z, okay, so maybe let's do it here. So phi plus is a 0, 0 plus 1, 1, okay? Now, if Alice applies locally a sigma z, so if you apply sigma z tensor identity on that guy, Well, on the 0 you do nothing, on the 1 you flip the phase, okay? So you get a 0, 0, minus 1, 1. Okay, so in this case, the state is transformed to phi minus. Now, if you apply an x, okay, then it's, you see an x is a flip, so you get a 1, 0 plus 0, 1. So you get a psi plus, and if you do the last one, you get a psi minus, okay? Now you see already the magic, right? The magic is that by doing a local transformation on Alice's side, the global state is prepared in 4 states that are mutually orthogonal, okay? So if they are mutually orthogonal, it means I can perfectly distinguish them via a quantum measurement, right? And the measurement that does distinguish them is the Bell state measurement. So now, so after the transformation, so first, okay, so there is this transformation here applied to that particle. Then that particle is transmitted through a quantum channel to Bob. Okay, so this is the, so send, this is sending the qubit of A. Okay, so Alice is just sending her qubit, there is just one, right? And so now Bob, he has the full state, okay? So, yeah, maybe let's continue like this. So now Bob has the full state. And so the point is via a Bell state measurement, he finds out what are C0 and C1. Okay, because if he finds that Bell state, well, then he knows that Alice applied a sigma x, so that means 1, 0, okay? And so on. So the moral of the story is that entanglement boosts the classical capacity. Ah, damn, today it's really... okay, I can reuse that. So, using entanglement, one can boost the classical capacity of a quantum channel. Okay, and this is what is called dense coding. Yes?
I'm just not sure I follow, because in this case we have 2 bits, and the point of saying when quantum bit contains 2 bits of information is that before receiving the qubit B knows nothing, and when he receives it, he knows everything, so it must have been the qubit containing 2 bits of information.
Yes, yeah, you can view it like this, yeah. Mm-hmm.
Okay.
Mm-hmm, mm-hmm.
Yeah, because before that we have to have 2 qubits to have to store the information in the way. So if, say, we had hard drives of qubits, we would still need 2 qubits to store 2 bits of information in this way.
Yes, if you want to store information,
Yeah.
you need 2 qubits to store 2 bits.
But to send it, you only need 1.
If you have this pre-shared entanglement, right? Yeah, I mean, you see, another way to view it is to say, so if I just have a qubit, okay, how much information I can encode in it depends how, how I can rotate in the Hilbert space. So from 0, I can rotate to 1, but then I just have to rotate back to 0, right? So then with just so if I just have a qubit space, I can only have 1 bit. But if I have a 2 qubit space, however, with the restriction of being able to rotate only locally, yet I can explore the 4-dimensional space. Okay, that's somehow the magic, right? Because just by doing this local transformation, I can really obtain 4 orthogonal states. And therefore, I have that thing. But of course, this thing works only if the initial state here is maximally entangled. Otherwise, it would not work. Okay. Maybe let me conclude with one thing, because with this, in fact, we can connect back to teleportation, and in fact, we can argue now that the amount of classical communication we had in teleportation, namely 2 bits, this is necessary. Okay, I didn't show you that. I showed you that you need communication, but I didn't show you that 2 bits of communication are necessary. Okay. So let's try to do that. That is, let's see if I remember the argument correctly. But the argument has to do with dense coding. Okay, let's see, am I able to do it now or not? Okay, yes, I think I'm able to do it. So I want to do dense coding. Okay, so I have this is my phi plus state that I will use for dense coding. And now, so in dense coding, I just send my qubit through a channel, right? Now, let me think that instead of the channel, I want to use teleportation. Okay, so I have another bell pair here, and this is the one I will use for teleportation. Okay, so now what I'm going to do is that I will try to teleport that qubit. Okay, in dense coding I have to send it. Okay, but now I will, try to be. I will try to be subtle here. I will just teleport that qubit, right, via some entangled state. Okay, now. So the point is, I know I can do that. I can recover the qubit correctly and therefore perform my dense coding protocol under the condition that I send 2 classical bits. Okay, this is the teleportation protocol that we have seen. So here it works if I send 2 bits. Okay. Now, so here there is no contradiction, right? I prepare an information, right, that is 2 bits, and Bob gets it in the end, but I have sent classically 2 bits. Okay? Now, you see that if I could do teleportation with less than 2 bits, I would be able to send classical information of 2 bits in less than 2 bits. Okay? And that is not possible, right? Okay, because entanglement cannot boost, the classical capacity of a classical channel, right? Do you get it? Sorry, I know this one, it's a little bit tricky. Should I say it again? Okay, I try again, no? So, remember, dense coding, it's the idea that by just sending 1 qubit through a quantum channel, I can send 2 bits of information, okay? Now, I will try to do my dense coding without a quantum channel, but with a teleportation, okay? So what I do is so first I put the information here. So here there is the information about C0, C1, okay? Like I did here. And now instead of sending that qubit, I put it in the Bell state measurement, and via this extra Bell state here, I perform my teleportation. Okay? And my teleportation gives me the correct final state here, right? Okay, so now, if it gives me the correct final state, it means I can, here on Bob's side, extract the two classical bits C0 and C1 that have been encoded in that state. Okay? And now, if I could decode these 2 bits of information by having here send less than 2 bits, well, that would be really worrying, right? Okay? And so that's why you see that I need 2 bits of classical information to complete the teleportation protocol, because otherwise I would have a way to, boost the capacity of classical communication in a way that is just impossible. Okay? Yes?
So in the first example of teleportation, we have to send 2 bits via a classical channel.
Yes?
With 1 bit of quantum information.
Yes.
Okay.
Yes, it's a good point, yes. So you see, quantum information, it's way more difficult to send, in a sense, right? So of course, you see, one talks about the capacity of a channel, no? Which is how much information you can send through it. So there is the classical capacity, how much classical information you can send, and there is the quantum capacity, how much qubits you can send. And of course, that is always, an upper bound, a lower bound to the classical one, right? But you're right. In general, it's much more difficult. All right. Okay, I stop here. So, are there questions? Well, we can still discuss afterwards.